Hello and welcome back to Atomic Math. Today we're going to talk about atomic structure and understanding electron configuration. So in order to understand electron configuration, we need to understand the structure of an atom. So if you look on the left, you can see a hydrogen atom. And a hydrogen atom is made up of a proton, a neutron, and an electron. Now, of course, these are not to scale at all. In fact, if we look, we can see that a mass of a proton is about 1.67 times 10 to the minus 27. A mass of a neutron is 1.67 times 10 to the minus 27, but the mass of an electron is like 9.10 times 10 to the minus 31. Now, those numbers are super tiny, so you may not even have a good understanding of how much smaller that is. So let's imagine it this way. The mass of a proton is roughly 1,836 times bigger than an electron. And even that is still really hard to imagine. So think of it this way. If an atom was the size of a football field, and the nucleus, which is made up of the proton and the neutron, that would be the size of a grain of sand, and it would be sitting on the 50-yard line. And the electron, well, that would be an invisible speck buzzing around the outside of the arena. So even if you made an atom the size of a football field, you could still not see an electron with your own eyes. So an electron, in comparison to a proton or neutron, is extremely small, but also an atom in general is just so much empty space. And I think that's hard for us to actually comprehend. But like I said, even the nucleus would only be like a grain of sand in the middle of this football field. Okay, so let's look a little further. Let's look at how electrons orbit the nucleus. Now, this example here, this is sort of the Bohr model, and this is not a very good representation of the way it's actually happening, but it's good for helping us understand the different energy levels. So the first level, the one that's closest to the nucleus, this would be called the ground state, and it has the lowest energy. The next one up would be your second level, so it'd be a little bit more energy, and then your third level, which would be even more energy, and then it would keep going. So each electron can be described by its 4 quantum numbers, and the principal quantum number, n, defines the energy level the electron is orbiting in. So for example, in the ground state, n would be 1. On the second level, n would be 2, etc. Now let's take a look at our quantum numbers. Let's just start with our principal quantum number, which is n, and it has values of 1, 2, 3, etc. The second quantum number is called the angular momentum quantum number, and it is given the symbol L, and it has values of 0, 1, 2, etc. that primarily describe the shape of an orbital, and it has a value of 0 to n minus 1. So our possible values are L equals 0, 1, 2, or 3. So when L equals 0, we have an s orbital, and it's basically a sphere. When L equals 1, we have a p orbital, which looks like this, and if it's L equals 2, we have the d orbitals, and if L equals 3, we have the f orbitals. Now, d and f orbitals get a lot more complicated. They don't look as simple as this is, but for a diagram, this is fine. Now, if we look at the table on the right-hand side, we can see that when n equals 1, the only possible value for L is 0. So at n equals 1, you can only have an s orbital. When n equals 2, now you can have 0 or 1. So on the second row, you can have a s orbital and a p orbital. And then when n equals 3, you can have an s, p, and d. And then when n equals 4, you can have an s, p, d, and f. Okay, let's look at the next one. The third quantum number is the magnetic quantum number, and it is given the symbol m sub l. It has values from minus l to plus l, and it identifies the orientation of the orbital. So let's look at our possible values. So when L is 0, our only ml would be 0. When L is 1, we could have minus 1, 0, plus 1. When L is 2, we could have minus 2, minus 1, 0, plus 1, plus 2, etc. So if you look on the right, you can see that when you have an L of 0, so that's your s orbital, there's only 1. Your p orbitals have 3, your d orbitals have 5, and your f orbitals have 7. So the fourth quantum number is the spin quantum number, and it is given the symbol ms. It has values of plus 1/2 for spin up or minus 1/2 for spin down. And there's something called the Pauli exclusion principle that says no 2 electrons can have the same 4 quantum numbers. So if we look at our table here, we can see that our s orbital only has 1 orbital. And if each orbital can only have a up and a down, that allows us to have 2 electrons. The p orbitals, which have 3, because they can have 2 per orbital, have 6 electrons. And then the d's have 10 and the f's have 14. And of course, this corresponds to what you would see on the periodic table. Now, they don't just fill these in a random way. Electrons are little kind of antisocial little creatures. They don't like to be close to other electrons. So if we look at a p orbital here, let's imagine that this is a p orbital. The first electron is going to go into the first p orbital. The next one's not going to join the other electron. It's going to go to the empty one. And the third one will also go to an empty one. Only then will they start pairing up. So as long as there's an empty one, they will fill the empties first before they start doubling up. Because as I said, they don't want to be close together. And then of course they will eventually come together. So let's take a look at a periodic table. Now this periodic table is not your normal periodic table. This one is to show you the way that the orbitals are. So you can see that a normal periodic table would have the F's underneath the main body of the table. But on this table, it inserts them so you can actually see where they are, so you can see how things are flowing. I always found that it helps for understanding electron configuration because you can see why and where things are. Of course, a regular periodic table is just going to look like this, and we're going to have our F orbitals on the bottom. Okay. So now let's look at electron configuration. If we have a periodic table here, let's say we wanted to look at hydrogen, and hydrogen is right here. It's our first element. We can see that it would just have one electron in it because it's the first one, and that would be simply a 1s1. Now, if we go to the second element, which is all the way over on the right, it is the helium, and that one would be right here, and that one would have 2 electrons, so that would be 1s2. Now, if we look at lithium, which we could find right here, lithium would be 1s2, 2s1. So now if we look at beryllium, which is right here, we would have our 1s2, but now we'd have 2s2 because we have 2 electrons. Okay, let's jump ahead a little bit so we're not doing every single one. Let's jump to oxygen. Oxygen is over here in the p orbitals. It's right here. And if we did that one, we would have a 1s2, a 2s2, and a 2p4. Let's look at another one. Let's look at silicon. Silicon is going to be right over here. And for this one, we would have a 1s2, a 2s2, a 2p6, a 3s2, and a 3p2. Now let's take a look at our noble gas. We will look at argon, and it is right over here. Now, if we follow through our method, we will find that we have 1s2, 2s2, 2p6, 3s2, and 3p6. Now, the reason why I wanted to show you argon is because a shorter method for this, because you can imagine as you get further and further down the table, these lines are just going to keep building and building. You're just going to have so many orbitals listed. We can always list the last noble gas and then just add on what came after that. So for example, if I want to express anything that's in row 4, I can use a short form where I show argon and then I only show what comes after that. Let's say I wanted to look at copper. So copper would be right over here. Now, based on our whole plan that we've been following, we would say that copper is the argon, and then after argon, we have a 4s2 and a 3d9. Now, that is what you would expect it to be. But of course, there are always exceptions, and in this case, copper is this. The d orbitals actually steal one of the s orbitals. And it's because having a full d orbital is more stable. So there's always going to be a couple little exceptions in there, and that's why I wanted to show you this one. So copper is actually 4s1, 3d10. But you can see it was a lot shorter because I was able to use the argon. You just put that in square brackets, and then you only have to give the configuration of the row that you're in. Okay, let's look at lead, which is down here near the bottom. So for that, we would need to know what our noble gas was before it. So xenon is the last noble gas before lead, which is right over here. So we can use that noble gas, and then we only have to give the configuration for what comes after xenon, and it would look like this. So xenon, and then 6s2, 5d10, 4f14, and 6p2. Now, sometimes you will see it reordered so that it goes from smallest number to largest number, but I think it makes more sense to see visually the order that you followed to get there. Now, a lot of times students will struggle with the order that they go into once you start adding in D's and F's. And there's a little diagram that helps some students. Here you can see it's sort of like this big sort of S chain. And if you just follow it, it will tell you which ones come next. So you can see that you have 1s, and then if you follow that around, you get to 2s, and then you get to 2p, then you get to 3s, then you get to 3p, then you get to 4s. Then you go back to 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. So this helps you, if you're trying to do configurations for the table, know exactly the order to put them in once you get further down in the table. Of course, up top, it's pretty simple, but once you get further down, it gets a little bit more complicated. So I hope that you found this video helpful. If you did, go ahead and hit like. And if you want to see more videos like this, hit subscribe, and I'll see you in the next video.